Okay, so hi everyone. Let me thank the organizers first for this very nice opportunity to be here. It's such a pleasure. And also Yevgeny Skvortsov for the participation in the invitation and all this. So I will speak about a project that I initiated and led in Munich. And I worked together with Tita Lust, Stefan Stieberger, and Stefan's student, Puria Mazlumi. And that is extracting by gravity from string amplitudes, string theory amplitudes. So basically, let me take you on a trip from field theory to string theory and back. In particular, we will start with spin 2 field theories, the particular case of bigravity, ghost string bimetric theory that is. Then we will move on to string theory and string theory amplitudes, scattering amplitudes calculations. And finally, we will extract from these effective actions, which will take us back to the field theory side and thus enable us to compare with the bimetric predictions in that regard. So let's start. Let's start with gravity, that is, namely Einstein's theory of gravitation. We think of it as a metric theory of space-time, but in fact, there is an alternative approach due to many authors that I enlist here, and that is that the Einstein-Hilbert action is the unique kinematics of a spin-2 field, spin-2 particle in terms of particle theory. And in fact, you can even do this simple exercise on your own. Just write all possible Lorentz invariant terms you can for a symmetric rank 2 tensor. And also impose that these, assume that these are local and impose that there are no ghost degrees of freedom, no unhealthy degrees of freedom propagating in these terms, including these terms. And in fact, it turns out that what you come up with is diffeomorphism invariance in the very end. So the alternative way of seeing GR is really a particle theory of spin-2 fields, massless ones, that is. Now, as we know, general relativity is not a quantum theory of gravitation, but in fact, it has some relation. The graviton that appears in general relativity also appears within string theory, which can be seen as a quantum theory of gravity as well. And how does this graviton appear? In the simplest case, let's take here the particular case of bosonic string theory, closed bosonic string theory, and look at the states. What we see is the first instance of massless states, the massless level as it's called in the bosonic string theory case, contains this state built out of two bosonic oscillators acting on the vacuum. And this state contains a symmetric and antisymmetric and the scalar representation of the Lorentz group. And in fact, the symmetric one was first proposed to be identified with the graviton by Scheck and Schwarz in 1974. That its interactions are further of the Einstein-Hilbert type was shown in these papers here by Green, Schwarz, Brink, and Gross and Sloan. And what they did was actually to compute, in heterotic string theory, if I remember correctly, string amplitudes in regard to the scattering of this very state, the graviton state that is built out of this. And from those, they extracted the effective action and confirmed, they computed the 3- and 4-point amplitudes and extracted from those the effective action and confirmed that it's the Einstein-Hilbert interactions, perturbatively at least, that this very state, the symmetric state at this level, interacts as. Now let's move on to extensions of general relativity as it's associated with open questions such as that of dark matter, dark energy, the cosmological constant. And in particular, let's, sorry, I moved way too far. Let me go back. And in particular, let's consider ghost-free bimetric theory. What this theory is it's an extension of GR in such a way that there are two rank 2 tensors, each of which has kinematics governed by a separate Einstein-Hilbert action. So you see two terms describing the kinematics of two disparate rank 2 tensors associated with two different Planck masses, a priori at least, and which are associated also further with two disparate diffeomorphism invariances. Now, there is further in this theory a scalar term, a potential with no derivatives, that describes the interactions of these two kinds of rank 2 tensors. And this potential breaks the two initial copies of diffeomorphism invariance to two. to the diagonal subgroup. So the whole action here respects one copy of different invariants, just like in general relativity. And you see further, apart from the two Planck mass scales that we have in front, you see inside some beta n parameters, dimensionless parameters that are associated with this potential and a priori are undetermined. And let's look at this, at the structure of this potential a bit closer. It is built out of the so-called elementary symmetric polynomials, some polynomials that are built out of traces of a matrix that has a particular form. It's this here. It's the square root matrix of the inverse metric, where of one of the two initial Einstein-Hilbert terms, multiplied by the other metric. So you have G inverse times F. You take the square root and you put it as an argument inside the elementary symmetric polynomials. And also remember the sum contains only polynomials of a specific order. Okay. Now, where was this action inspired from? It was inspired by DRGT theory, Deram Kabadadzi-Tolle. And in particular, what they did, these authors, was to write for the first time a fully nonlinear massive gravity action. So they extended the Fitzpatrick result that was first written decades ago around Minkowski spacetime, around arbitrary backgrounds. They extended it. And for that, they used this particular matrix, built out of the matrix, the metric G, and an arbitrary reference metric that in their case was assumed to be the Minkowski one. So as further the degrees of freedom are concerned in these cases, we know that GR propagates 2 degrees of freedom. And in massive gravity, in both the Fitz-Pauli and the DRGT theory, 5 degrees of freedom, so 3 more are propagating. But in fact, in ghost-free bimetric theory, 7 degrees of freedom propagates that do not, around arbitrary backgrounds, split into those of a massless and a massive graviton, so in 2 and 5 degrees of freedom. It's only around particular vacua that the split can be understood. All right. So when I moved to Munich, I started thinking about this theory and what we can actually, what kind of concrete predictions we can make about this theory from more fundamental framework such as string theory. And so initially I was thinking how we could extract information on the potential I showed to you with the elementary symmetric polynomials in the previous slide, from string scattering amplitudes. So with Dida and Stefan's student Puria, we devised this plan. At first, we had to expand bimetric theory around a particular background. And why that is? Why is that? This is because in the string theory side, or in general, when it comes to scattering amplitudes, in the legs of the amplitudes, you always put some well-defined states that have well-defined mass and momenta. However, here, what happens is that the two metrics, in a convoluted manner, correspond, at least around specific vacua, to masses and massive degrees of freedom. Here, in this action, when I'm given this action, I don't know which are the massive and which are the massless degrees of freedom that are propagating. So I just see G and F that interact. So first, we had to choose a particular vacuum and expand so as to come up with states that are mass eigenstate of the mass matrix of the theory around a specific background. Then we had to find the correct correspondence between those states, or in the particular background in the field theory side, and states in the string theory side. So we had to choose from the infinite towers we come across in string theory, which are the most suitable candidates to describe the states we have in the field theory side. And then we had them interact and compute the on-shell tree-level amplitudes that correspond to their scattering in step 3. And finally, extract from them, and for the first time, extract Lagrangians from string theory amplitudes that involve massive spin-2 states in the external legs. Extract that is the effective action and compare with what bimetric theory gives us. The first non-trivial case in the side of in the field theory side is that of 3-point interactions, so cubic interactions, which meant that, of course, we had to start with 3-point string scattering amplitudes. All right, so step 1 is to expand. And for that, we looked at the literature. There was already during expansion around Minkowski spacetime, the so-called solution of proportional backgrounds in bimetric theory, where one of the two metrics is taken to be proportional to the other one in the background. And we chose the particular case of Minkowski to simplify the situation. And so you see that both are expanded around Minkowski. Here we have the two fluctuations, delta F and delta G of the original metrics. And it turns out there are two mass eigenstates, the G capital and M capital. And here I give you the quadratic actions that the two G capital and M capital obey. So what do we have here? This epsilon calligraphic hat that I give here is nothing other than Lichnerowitz operator. And if you remember, the Lichnerowitz operator is the linearized Ricci scalar, the derivative part of the linearized Ricci scalar around Minkowski spacetime. So capital G, behaves exactly like the graviton, the Fitz-Pauli graviton around Minkowski spacetime. Further, the action of M at the quadratic level is this one. So again, kinematics of the Fitz-Pauli type, so just like the graviton. But there is further a mass term, again, precisely of the Fitz-Pauli type, and this is exactly as it should be, because Fitz-Pauli showed that this is a unique term that does not propagate those degrees of freedom around Minkowski spacetime for rank 2 tensor. Right. In the particular case of bimetric theory, this mass here that is arbitrary for Fitz-Pauli is related to the parameters that enter the bimetric action, so the two Planck mass scales. Here, alpha is the ratio of the two Planck mass scales. And beta these three beta are some of the beta that appear originally in the bimetric potential. Right, so we have a massless eigenstate and we have a massive eigenstate, both with healthy kinematics. And the massive one was in fact proposed in these papers here to be a viable dark matter candidate, and its phenomenology in this framework was studied. And in fact, its mass was constrained to be no more than 100 TeV. So this is a plausible scenario. So what do we have here in terms of motivation? We have a theory with two metrics originally that somehow is exotic in that regard. But around Minkowski, we see that we have the graviton and another particle that may account for dark matter. Now, when it comes to cubic interactions, because these are the ones we're going to consider from the string theory side as well, as I told you, they involve very many terms. So here I give you just one example, the interactions of the G capital, remember the graviton, and two further M square, that means two further massive spin 2 fields that may correspond to dark matter. So this is just a field theory prediction I give you here for these kinds of interactions. And it's very hard to know what to expect from the string theory side. But let me actually list for you to understand all kinds of interactions that we get to cubic order around Minkowski from ghost-free bimetric theory. So for G, the graviton, we see that its self-interactions at the cubic level do not contain any zero derivative terms, as should be the case, because this is to be identified with the graviton also at cubic order. And further, there are two derivative interactions, self-interactions of G capital, but they're precisely the Einstein-Hilbert type. Now, the massive spin 2, also at cubic order, when it comes to derivative self-interactions, behaves very much like the graviton, but it also comes with no derivative terms. So this is something that is associated with its mass. And further, we have the interactions that I showed to you in the previous slide, this big, very long equation, where we find both non-derivative and two derivative interactions of the graviton and the massive spin 2 field. So what we see is that at cubic order, G, that is the graviton also in this order, obeys the theorem by Boulanger, Damour, Gualtieri, and Henault, according to which massless gravitons may only be associated with Einstein-Hilbert interactions, not other kinds of potentials. Further, what we see is that all kinds of vertices written at cubic order depend in a non-trivial manner on the parameters of bimetric theory. So remember the two Planck mass scales and the beta n parameters. Now, what is a distinguishing feature of bimetric theory is that at cubic order, at least, there is no kind of interaction that involves two gravitons and one massive spin 2 field. And this experimentally, at least to cubic order, may serve as the absence of such signals may serve as a hint that this there might be some truth to this theory to cubic order. Right. Now we have all terms from the field theory side. Please go ahead. Yes, certainly. Very good. So you right, okay. So this action here, the sole requirements to write this action are first to have one set of TFOs respected, so to preserve one copy of TFO invariants, and further to have no ghosts, any particular ghosts of the Ostrogatsky type, so box square, unhealthy degrees of freedom propagating. So with these two requirements, the only kinds of terms to cubic order you can write are these, precisely because, I mean, at least when it comes to interactions of G with M, precisely because ghost-free bimetric theory is unique in respecting those two assumptions. All right. So I sketched for you how all these kinds of interactions to cubic. Please go ahead. Yes. Yes. No. One more or okay. Okay, in principle it can, but then again, this is. Oh, sorry. Yes, I forgot. So before we had this question as to whether there's how unique the cubic order terms are, and now we're having this question as to whether the Planck mass can be set to 0 upon choosing specific values for the beta parameters of bimetric theory. So in principle, we can do that, but in fact, we want to extract information on the potential. So if we go to the most if we assume limiting a limit of this theory that has just two rank 2 tensors non-interacting and that are both of the Einstein-Hilbert type, then we don't get much further than the Einstein-Hilbert kind. We want to see if we either massive extensions or extensions involving this potential. So we assume that it's a choice that the Fitz-Pauli mass does not vanish in this case. But in principle, good. Yeah. Yeah, so the question is though that can you, by choosing specific values for beta, can you actually have two gravitons non-interacting, that is? Non-interacting, yes, yes. So, well, if you make that choice and you don't have a mass around Minkowski, then you just have two gravitons, that is. If you go back to the fully nonlinear case, you might still allow for some interactions, having said the Fitz-Pauli mass on Minkowski, but then again, that's a nonlinear background. Now, the thing is, if you try to set parameters naively to 0, then you might raise some strong coupling issues. Right? Yeah? Yes, yes. Yes, yes. Yes, 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 yes. That's fine. No, the beta themselves, you mean? You can set the sum, but not the beta. Yes, yes. I'm not saying you cannot do that. That's not what I'm saying. What I'm saying is that we want to have a massive one, and we want to look at it. Now, what you, from what I understand, what you want to investigate is if you do set this equal to 0, and then you go back, and you still you go to the nonlinear theory. That is, you have to somehow redo their packaging in Einstein-Hilbert actions, which I don't know. You have to do it anew, and then you're saying that you might still have betas there that are not. It is. So initially we have 5 betas. Okay, we have beta 0 and beta 4 that account for cosmological constants of the 2 metrics, and we have the other 3 that, as you just observed, appear there. Now, in principle, you can have them. They're not constrained to be anything. They can be 0, some can be 0 or whatever. And this does not break neither DFOs nor the structure of the potential that guarantees the absence of the Boole-Ward Desert ghost. And in principle, you can absolutely very well also have that. But it's not interesting for us. I'm not saying that it's not possible. It's just that it goes, it does not yield something that we can measure. The Fitz-Pauli masses we're going to see, we're going to be able to relate or try to relate to something in the string theory side. Here as it is, if you go back, the 3 parameters, if they don't enter an object that a quantity that we can measure, they're not of little use, at least to tree level and to cubic order in this particular case. Yeah. Mhm. Yes, so these limits have to be taken with a lot of care. It depends on how you want to take this limit. I mean, do you want to do what Xavier is suggesting, or also take limits on the Planck mass? Yes, so by tuning the ratio of the two Planck masses, it's possible to either get GR or massive gravity. So the two limits. So here the ratio of the two, which is mg over mf. If it goes to 0, you get GR. If it goes to infinity, you get massive gravity. But these limits have to be taken with a lot of care. So if you actually do set alpha equal to 0, then it means that you're raising for the other metric, so strong coupling issues. So if this theory tells you that there is some limit, but whether that's well defined and to what extent, I am not sure I can answer. Which is why we're not going to assume anything for this. We're going to stay in a region of the parameter space where both metrics play a role and none is decoupled. Yes, that's true. But the thing is, it wouldn't, if you start assuming these things on the Planck masses, then they wouldn't be interacting. You can, sorry, where is? Yes. So if you send this away, the full potential, they still respect your theorem if you want. With so it's perfectly, yeah, fine. Who was I? Yes. Okay. So now we're ready to compute string theory amplitudes and try to compare with bimetric theory. But the thing is, at least to the best of my knowledge, the only kinds of amplitudes we can compute in string theory are of the on-shell kind, on-shell scattering amplitudes, which means that in the legs of the scattering amplitude, you only put on-shell states, namely string states that are created by vertex operators that satisfy particular on-shell conditions. And what do these look like? They look like these conditions, namely that the mass has to be on shell, satisfying the equation of motion, and further that the field has to be transverse and traceless, and TT as I'm going to refer to in the following. So we're only going to deal with these kinds of states from the string theory side, which means that if we want to have any hope of comparing with a bimetric theory, we need to impose these conditions on the field theory side as well. And in the field theory side, what are we to expect? What are we to impose on the cubic interactions I showed to you before? The massless Klein-Gordon equation for the graviton, the capital G, that further satisfies transversality and tracelessness, which leads to two propagating degrees of freedom. Remember, we have one Defoe invariance associated with this capital G. And further, we have the massive Klein-Gordon equation governing the kinematics of M, the massive spin 2 field. Further, transversality and tracelessness can be imposed, but there is no residual gauge invariance in this case because the mass term breaks in this particular background the other Defoe invariance, which means that we're left with 5 propagating degrees of freedom. And in here, in this particular case, you see the split of 7 to 5 and 2. Both have to satisfy the massless or the massive Klein-Gordon equation and BTT. And it's all these equations that we have to impose to our cubic interactions so as to be able to compare with the string side, which brings us to this, which brings us to something much simpler. For example, let's look at the GM square interaction. Remember that very long equation I showed to you before. It is reduced to these two lines of interactions. And then we have G self-interactions and M self-interactions. Right, so these are the on-shell terms that we get at cubic level, at cubic order from bimetric. And where is information that might take us to the potential here? It's only here that we see the beta parameters, only in the non-derivative self-interaction of the massive spin 2 that we have some beta parameters in the coefficient in front. Okay? For all other terms, the information has disappeared. I mean, terms that were containing this kind of information have disappeared because of the on-shell conditions. So let's see what we have. We have only these four, so just beta 1 and beta 3 entering in the end, nothing else. And of course, the two Planck masses. And we have only in the case of the self-interactions of the massive spin-2 field, a non-derivative self-interaction. In the case of GM square, one graviton, two massive spin-2 fields, so there is no non-derivative term that remains after imposing the on-shell conditions. However, what you further see, if you want to sit down and think about these terms, is that these are all possible, in fact, Lorentz invariant terms that you can write to cubic order for TT fields interacting, and also assuming, this is an assumption now, that G square M, there is no G square M to this level, to this order in this particular case. And remember, this is the unique discriminatory feature of bimetric theory. Everything else we see here could have come, in principle at least, from another kind of bimetric theory, respecting Lorentz invariance. Right. Now, what is unique, however, is, as I told you, the coefficient in front, the M cube, the trace of M cube, the non-derivative self-interaction of the massive spin-2 field. So we still have hope that after we compare with string theory, we might extract information on that from the string theory side. Okay. So we're ready to start computing string theory amplitudes, but for that, we first need to do the correct identification of the states, the two mass eigenstates, G and M, that we have in the field theory side. And as must be clear, it is well known, and as I showed to you on the first slide, the graviton is universally identified with a massless state, massless symmetric representation that appears in closed string spectra in all kinds of string theories. So for that, we have no doubt, but we have to identify the massive spin-2 field. And in a somewhat, if I may say, existential manner, the question raises itself as to whether this is an open or a closed string state, this massive spin-2 field. And what we did, drawing motivation from previous work by Dita with Ferrara and Quejallas, was to consider the open string spectrum, and in particular, the level, the first massive level that you encounter in type 2 string theory, where you have these kinds of oscillators acting on the vacuum and building a massive spin-2 state, and actually in a rank 3 tensor as well. And the whole level has mass in the string side that is proportional to 1 over alpha prime, is actually equal to 1 over alpha prime, where alpha prime is now the string scale, not to be confused with alpha. So if we indeed choose, identify our massive spin-2 from the field theory side with a symmetric representation that is built out of these oscillators at this level, then we are forced to assume that the Fritz-Pauli mass that comes from the field theory side is equal to 1 over alpha prime. And we will see whether this makes sense to assume. We have to look at the interactions as well to see if this will make sense. As I will also come to in the very end, we're currently investigating other cases, for example, the closed string spectrum, and whether that could describe the massive spin-2 state. All right. Yeah. So I start here with a master formula for a tree-level disk on the disk scattering amplitude involving both open and closed string states, because we're going to compute also the amplitude corresponding to the interaction of G with two M's. So inevitably, we're going to have one closed and two open string states. And the master formula is this. Namely, it's nothing other than an integral of the correlation function of vertex operators that correspond, as I told you before, to the string states that we will put in the external legs. And the integral is over the world sheet that depends on the particular amplitude. Now, particular cases of this were investigated in the 90s when it came to massless external states. And further, thank Dita and Oliver Slaughter and Stefan and Taylor, they investigated and computed a particular case where you might have a massive state in the external legs, but all others were assumed to be massless. So we we came across two novelties in our own work that had never been encountered before, namely that all our external states are going to be rank 2 tensors, either the graviton or the massive spin 2, and that in our cases, at least two of the external legs are going to be massive, because remember, it's these three amplitudes we're going to compute. So here we have the graviton. Okay, this had already been computed before, so we're not going to need to compute that. But these two cases that we're going to compute, they contain at least two massive spin 2 rank 2 tensors. Right. And in fact, it turns out that these two points significantly complicate both the computation and also the extraction of the effective action. All right. So to start, I give you here the expressions of the vertex operators. For the graviton, it is well known. It takes this form. Namely, is a conformal field that depends on the worldsheet, on the space-time parameters, and the polarization tensor, and worldsheet, I said correctly. The polarization tensor and the momentum of the particular state that the state is thought of as having. And you see here the various, the coordinates, the worldsheet coordinates, fermionic and bosonic, that we have in this kind of string theory that depend on the worldsheet coordinate. So this particular vertex operator is thought of as creating on the particular point z, z bar on the worldsheet the graviton subject to these conditions if you want. And you see Q is being its momentum of the state. This is transversality, this is masslessness. This is just the fact that it's a symmetric representation of the Lorentz group, and this is tracelessness. So already you see the on-shell conditions that I warned you about before. That this vertex operator, consequently, the state has to satisfy. The massive spin 2 vertex operator was constructed in these references, and I give you two kinds of expressions of it. Why is that? Because vertex operators can be written in different ghost pictures. And in fact, it doesn't matter which one you choose, so long as you respect that the sum here of ghost pictures of ghost charges that each vertex operator is associated with cancels the background charge of the disk. So namely, that the whole thing is Beerstein invariant. So depending on what kind of amplitude you want to compute, you're going to need different kinds of pictures of the vertex operator corresponding to a particular state. But the state is unique, and the vertex operators can be infinitely many, describing the very same state. You see further, again, the on-shell conditions, namely K now being the open or massive, if you want, string state momentum. So transversality, alpha is the polarization tensor of that state, the mass shell condition, symmetricity, and also tracelessness. Okay. So with these tools, we're ready to compute the first amplitude, so GM square, 1 graviton and 2 massive spin 2 fields. And it takes this very form. It is, as I said, an integral of the correlation function of the three vertex operators. So massive spin 2, and graviton. And the massive ones have been chosen in such a way that the sum of the ghost, this is a ghost charge, sums to -2. That is required for Beerstein invariance. Now, these kinds of the open string is thought of as being part of the tower that is formed on the deep brain within this field theory, string theory, sorry. And this brain is thought of as being infinitely heavy, which means that momentum conservation only makes sense along in the brain directions. And in fact, in our case, this won't matter very much because we're going to consider brain filling, space-time filling brains. So in the generic case, remember K1 and K2 correspond to the open string state, so massive spin 2, and Q corresponds to the closed string state, so the graviton. And momentum conservation along the brain takes this form. Here, we use only that component of the closed string momentum that is along the brane, has direction along the brane. And how does one obtain this component of the closed string momentum? One does it by using the D matrix. The D matrix is it has two indices, and it contains information on the boundary. So it tells you how the closed and the open string roughly interacts when it comes to boundary conditions. And so with this matrix, you can build the parallel and transfer to the brane component of the closed string momentum. It is only this one that you insert in the momentum conservation expression. Now, as I said, this is a 3-point amplitude from the string theory perspective. But then again, because of the fact that there is a boundary and because of the fact that we can split the closed string momentum into two, we can think of it as a 4-point amplitude kinematically, and also within the correlation functions, as we will see. So in fact, we can define the STU variables, the Mandelson variables, regarding two open string into the two components, so to speak, of the closed string momentum. And it turns out, if you use all the kinematic relations that you can show that there's only a single kinematic invariant describing this process. For example, it can be S related to K1 K2, the open string momentum. And I remind you, alpha prime is the string scale. Okay. Now, how does one go about computing the full GM square amplitude? One puts in that expression I showed to you here, this correlation function. One inserts the expressions of the vertex operators that are huge in total, and starts performing extensively Wick's theorem so as to compute the final result, using also the correlators of the the X mu and psi mu on the disk. They have specific correlation functions on the disk, 2-point correlation function. Right. And so we plug in and we start computing the contractions. And then we also have to fix the symmetry of the world sheet in this particular case by fixing the positions of 3 vertex operators and also inserting the C ghosts. We can discuss that these kinds of ghosts are very different from the ones I was mentioning before. They're reparametrization ghosts. We can discuss it if you'd like. And in the end, what you're left with is nothing other than an integral over the real line. We have managed to reduce it to an integral to the real line. And very long expressions that contain dependence on the kinematics of the scattering process that we have. And in particular, the full amplitude is given by this expression here. So you see 2 means we have 2 open string states, 2 massive spin 2 states, 1 closed string, the graviton. And here you see, apart from the parameters in front and the gauge group factors in front, we can discuss it as well in the end. You see a sum of 4 kinds of terms. I give you the simplest example here. And the way you actually write the sum doesn't much matter. It's just a matter of convenience. We have just chosen to split our terms in this way. Just by looking at the power to which 1 over x1 minus x2, x1 and x2 being the insertion points of the 2 open string states on the world sheet. So for example, A4 means that all these kinds of terms that I give to you here, they come from contractions that in the denominator have x1 minus x2 is the 4th. It's just a way of packaging the terms conveniently. So this is the simplest kind. We get many 4 packages. And this is the simplest kind I just give you here, just to get an idea. You see in front the 3 kinds of polarization tensors. And you see that it's an integral over the real line. And you see here these kinds of terms with indices. And again, I give you the simplest example. So A with 4 indices is this big expression here. It depends on momenta, all kinds of momenta of the external states. Remember, it's a 3-level amplitude. And the D matrix as well. The boundary, the matrix containing the information on the boundary, as I told you. And in this case, we have organized all terms in powers of alpha prime. This is going to be useful in when it will come to the extraction of the effective action. So again, these are the simplest ones. And in fact, we have computed all 36 kinematic packages that are that have longer expressions, which you can find in the paper as well in the appendices, if you'd like. And remember now that all kinematic packages, they are exact expressions in alpha prime. We have not performed any kind of truncation or expansion in alpha prime. They're exact. So we have the full amplitude. Now, if one further performs partial fractioning and starts evaluating the real line integrals that one encounters, we arrived at this final result, for example, for the case of A4. And you see that kinematic packages get combined, so to speak, into one kinematic package after computing the integrals. And you see here gamma functions appearing in products within products and ratios. Schematically, we have something that describes the kinematics that comes from the numerators, namely, after performing the contractions within the correlation function. And then you also have what comes from the integrals, the value of the integrals, that is. Okay, so basically, for example, here in the particular case of A4, you have kinematics in here times value of the integral that contains the gamma functions. And remember, this is just one of the 4 kinds of terms that enter the final result of the full amplitude. We give the expression in the paper, and it's valid actually in all kinds of all cases of space-time dimensions, so both 4 and 10D. I can argue why later if you'd like. And further, we computed also the amplitude that corresponds to the scattering of 3 massive spin-2 states, so 3 open strings, which is much simpler. And in the end, its expression is nothing other than what I give here. Now, because the 3 graviton amplitude had already been computed in the literature, it's well known in many kinds of theories, heterotic closed strings, and so on. It is instructive to actually, and that's what we did, to compare it, the M cube with G cube. So the 3 massive, the scattering amplitude corresponding to 3 massive state scattering, and the one corresponding to 3 graviton scattering in string theory, both in string theory. And we know that the one corresponding to the graviton respects the Theos. We know, as I told you in the very first slide, that amplitude will respect diffeomorphism invariant because it yields part of the Einstein-Hilbert action. Yes. What do you mean? Yes. Q is the momentum of the full state. Okay. So in both the field theory side and the string theory side, we have a state has a momentum Q. Yes. Oh, you mean you find it confusing to define Mandelstam? Okay, it's one way of actually computing the amplitude, but you don't have to if that's what you're asking me. You said that traditionally everybody did it this way, also like Klebanov and Hashimoto, they also did it. But the thing is, you can perfectly well write your conservation condition using these Mandelstam variables, just because you can split the momentum using the D matrix. Nobody tells you not to. Both Q and DQ correspond, Q parallel and Q transverse correspond to the closed string momentum. You cannot split when you think of the state. The full state has momentum that is Q. It's just that it splits into these 2 components, and only one enters the momentum conservation. In our particular case, because we want to compare with Bigravity, which is 4-dimensional, we will restrict ourselves to 4-dimensional branes. So both the spacetime and the brane will be 4D, and the branes will be spacetime filling. So in fact, momentum conservation along the brane, in our case, reduces to momentum conservation in the full spacetime. It doesn't matter anymore. Right. Okay, so as I was saying, the graviton, 3-point graviton amplitude in string theory, we know that it respects the Theos, and we have its full expression, and we compared it with the 3 massive spin-2 amplitude, and we already at this point saw an issue. And what is that? If we disregard the first line, which will give rise to non-derivative terms, so all all the stuff that comes because the mass of spin 2 is massive. If we just regard the kinematic part, these lines, these two lines, the two derivative interactions, or two momenta, if you want, because here I give you the amplitude and not the action, are precisely the same as that of the graviton, the three graviton amplitude in string theory, modulo these three coefficients. So let me repeat that. The two momentum terms of the graviton and of the massive spin 2 in string theory, the open massive spin 2 in string theory, are precisely the same up to a coefficient. And this already tells us that the extracted action from this amplitude will not respect the Fos, because it's only the graviton coefficients that actually do. Anyways, moving on. We want to extract the actions out of gm square, the amplitude that we computed for gm square, and m cube. And for that, we first do some simplifications. So in fact, we take the simplest possible case for T, which means reducing to space-time filling branes. And we also assume this very simple choice for the gauge group, just it being a U1 gauge group. And to extract the effective action, one makes a standard replacements of the polarization tensors and momenta with fields and derivatives, as usual. Now, the thing is, all other kinds of actions that were extracted from string theory, they were in the purely massless case, and one knew what exactly to do. In our particular case, we have masses in the external legs, in most of the states that we use, that depend on alpha prime. So the string scale that is taken to have a limiting value when extracting Lagrangians in the massless case now also appears within our masses. So we have to take the limit with care. And now to do this, to see this and exactly how we should proceed, let's look at some kinematic objects. So for example, this alpha prime k1 dot k2, remember alpha prime is a string scale, k1, k2, the two open string momenta. This combination, if you remember, I also give it here, is part of the S of one of the Anderson variables that we have. And what you see, because K1 and K2 square go like 1 over alpha prime, what you say is that the full object here is, it becomes a further 1 for alpha prime being very small. So for the low NG limit, because the low NG limit is thought of as taking alpha prime to 0 when it comes to extracting actions from string theory, this object becomes dangerous within S. However, at the same time, if you look at this object, so one open string momentum times one closed string momentum, you see that this is well behaved because Q square doesn't depend on alpha prime. It's one, it just goes to 0. So this whole object is well behaved. And this tells us that if, remember the expansions, the kinematic packages, and the full expression of the amplitude depends on the Mandelstam, and in particular, for example, on S. If we truncate what we get using S, using this expression of S, then we will have stopped at some order and we will be left with something that is dangerous, that becomes of order 1. So the truncation will become meaningless, which means that we have to choose something else to parameterize our S. And in fact, we rewrote S using two, one open string and one closed string momentum instead of two open string momenta, such that the full thing is well behaved. And then if you substitute into the amplitude for S, you can truncate whenever you want, because every term within S is well behaved. So in fact, we substituted using this expression for S in the result of GM square. The final result of the one closed two open string state amplitude up to two derivative, two momenta if you'd like, is this. This is what we found after this substitution and truncation. And from this, we managed doing the replacements that I told you of the polarization tensors and momenta to extract the effective action. So we have, these are our results. This is G cube. This is exactly like the graviton cubic order, like what you get from any other kind of string theory. It's exactly the same with respect to Fos, no need to worry. For GM square, this is what we find. And for M cube, this is what we find. So for the cubic self-interactions of the massive spin 2. And now we can compare. Now we're ready to compare. And if you remember, and it's hard to remember, but I'm telling you that the coefficients that I showed you before, let me actually go back just to convince you. Here, the Bimetric cubic order interactions. We have a 2 here, and we have a 2 here. Everything else is precisely the same. If it weren't for this discrepancy here, this discrepancy here. So what we find is, what we compute is the interactions of this open string state we use with a graviton, and that's all fine, but it doesn't describe the cubic order interactions that appear in bimetric theory around Minkowski. Okay? And in particular, because we know that the cubic interactions, self-interactions of any field, when it comes to the 2 derivative terms, have to be of a particular type, the graviton type, for that to respect DFOs. What we understand from this is that the open string state that we have used does not respect the ferromorphism invariance. So there's just the graviton, the closed string graviton that respects DFOs and nothing else. And it interacts with this open string state. It can interact if you please, but not in such a way that you might be able to nonlinearly perform the sum and find and come up with 2 diffeomorphism invariances broken to 1 by the potential. Right. So this is basically the question, or sorry, this is basically our conclusion that both GM square and M cube, they the interaction terms are precisely the same in both the string theory and the field theory prediction up to coefficients. So if it weren't for the discrepancies, it would be fine, but we do have them. And the discrepancy is a sign that that the open string state does not respect diffeomorphism invariance, and nobody tells us that it should, by the way. Also, as a side comment, what is interesting to note is that in the case of the self-interactions of the massive spin 2, we find the 2 versus 3 discrepancies. So 3 is in the string theory side, and 2 is what comes from the Bimetric side. And in fact, this is strikingly reminiscent of the Van Dam-Veltman-Zakharov discontinuity, in a particular manifestation of which the graviton propagator, the massive spin 2 propagator, in its massless limit, actually takes this form, where there's a 1/3 in the second term, which in the case of the massless graviton is a 1/2. So instead of a 1/2, we have 1/3 for the massless limit of the massive propagator. But then again, these 2 discrepancies, our own and the VDVZ, are very different in nature, because in our own case, it is a sign that DFOs are not respected by this open string state, whereas in the VDVZ case, the 1/2 versus 1/3 discrepancy is just a sign of the fact that there's a mass term. Okay, so what we gather from all this is that the open string state that we have used is not a suitable state to describe the massive spin 2 field. However, we have the full interactions that describe for this open string state with the graviton, which are perfectly fine and stand in their own right. And at the moment, what we're investigating is the case of the closed string state. So the massive spin 2 coming from the closed string spectrum and how this interacts with the graviton. Thank you very much.
So are there some questions?
So you said like you compute these 2 orders in alpha prime. But for string tension, is it 3 level? Is it a 3 level?
On the disk, the world is a disk. So you have many terms that depend on alpha prime. And you can perfectly well have all of them, don't truncate, because it's not a perturbative. It's a term of the perturbative expansion. It's not the fruitful or the first 3 level that you have, and for that we can compute everything. Now this gets arbitrarily many corrections from groups and so on. So
and the good of corrections from loop string would affect this coefficient?
That's a very good point. In principle, yes, absolutely. But this I cannot answer in practice because we have not performed the computation. Even this is hard to get, the tree-level computation.
Sure, I appreciate that. Another question, if I can. Can there be other massive spin 2 states in the subleading rigid trajectories of a string that could also contribute to the coefficient?
Yes, that could contribute.
You could mix these states with the one that you considered.
Okay, 1 second. So first of all, there's infinitely many. Okay, so in the full power. But at the same time, it's perfectly fine to just isolate one. Take that state and put it in the leg of this figure in amplitude. Nobody tells you not to. That's how people also compute amplitudes in string theory. Now, from that, you can extract the reaction. For example, you can get stuff like what they code. Now, you're saying that if I do the same thing for another state of the tower, that is again massive in spin 2, that state might mix. That other state will have a different mass. It's not the same mass. They're all massive after the first thing, but there's a coefficient across. So it's 1/4 prime. Then you get, depending on which string theory you are in, you get an integer times 1/4 prime. So it's never the same. It's never the same state. So it would tell you that the graviton interacts with more massive spin 2 fields, but those are different mass eigenstates.
Other questions?
Okay, maybe this is naive, but so you seem to tell us that if in the first scattering you get a different coefficient than in the theory, which is supposed to be more or less unique by ghost freeness, if I understood it right. So does it mean that the string theory has ghosts, or why not?
Okay, that's an excellent question. The massive spin 2 state that we use has a mass square or momentum square 1/4 prime. Okay? It is assumed, or if you want, we assume that the propagator of this state is well behaved. But then again, in string theory, at least in these kinds of descriptions, you don't deal with propagators. I don't know about string field theory techniques. There, the situation might change. So we consider a state that we think of it as having a well-defined propagator, but we don't really deal with propagators. Now, the ghost in the field theory side appears only if there's an issue at the propagator level. So only if you have things like box square. So what we find is not box square, but at the cubic order something that does not match. And this just tells you that you cannot resum all the orders to reach it. This is the only thing that it tells you. It does not necessarily tell you that there's a ghost, at least of the Ostrogatsky type. If there's another ghost of a different type at some order that may appear at some order, this I cannot exclude.